So welcome. In this evening's lesson, we'll be treating circulatory and oscillatory motion. So we are currently in week 7 from our 16 weeks night class. So we are in week 7. I don't know, from our previous class, I gave assignments. I did not really see any response yet. I don't know what was the issue. Okay, I would assume that probably, what would I even assume? I don't know what I would assume, Sha, but let's just believe that you guys would take the assignments seriously, or probably you would study the assignments for exam purpose or for knowledge sake. So we'll be heading into this evening's lesson, and for this evening, we'll be treating circular and oscillatory motion. Circular and oscillatory motion. So first off, I think I would start by listing out the objectives, what you should know by the end of this lesson. What you should know by the end of this lesson. So I think by the end of this lesson, we should be able to explain the concept of angular kinematics, torque, and moment of inertia. So all forms of angular kinematics, you'll be able to explain most of, if not all, the parameters involved in angular kinematics. You should be able to have their formulas, and also you should be able to understand the applications of centripetal force in circular motion. You should be able to define and analyze simple harmonic motion, conduct and interpret a simple pendulum experiment, and also relate theoretical principles to real-world experiences. So let's go to the real part. So as we said, the topic for this week is, let me go back. So I'll start with the definition from, or an explanation from the topic. The topic is actually talking about circular motion and also oscillatory motion. I don't know if most of you remember that at one of our lessons, we talked about different types of motion. We mentioned random motion, we mentioned translational motion, we mentioned stuff like oscillatory motion and so on. So in this one, we'll be focusing on circular motion. So circular motion and oscillatory motion, they are kind of similar, just that they are similar in the sense that they move to and fro about a particular point in a way. Circular motion, it moves around a point within an axis. It goes through the same path around an axis. While oscillatory motion, it moves to and fro along a particular path. So we'll be seeing some calculations under it. So first, I would explain what angular motion is. Angular motion, a body is said to be in angular motion when the body is rotating around a fixed axis. Once this angular motion is similar to circular motion, you have a single line drawn in space, then a body will then be moving around that single line. So there is this belief that when something is moving around or moving in circles, there's an angle at which it is making that motion, and that angle has is kind of like a tangent to the circular path that it is following. So what does this mean? If you had an object moving in a circular path, if you draw a straight line just on any path and let the straight line touch the surface of the circle, just the outer surface of the circle, let the straight line touch that angle, there's an angle that that straight line will make with the outer surface of the circle. That angle is what they use in determining the angular motion, and that angle is called angular displacement. It's called the angular displacement. So assuming we had something like a circle, then we drew a straight line passing, like, let's assume these are angle. Let me highlight something. Assume this my blue line now is the straight line. Then we had a circle that went just like as if the circle lapped on top of this thing, just lapped up on top of it. So there's an angle between the circle and the straight line. There's going to be an angle here. So that angle is what they consider when they're talking about angular motion. And they say that angle is known as the angular displacement. So, and it's usually measured in radians. And there is also a parameter, since it's in motion, when you hear that there is displacement, the next thing that should come to your head is velocity. Remember in our lessons when we were talking about elder brother being acceleration, younger brother being velocity, then the the youngest being displacement. So for circular motion or angular motion, we also have the same thing. We also have to look at both acceleration, velocity, and displacement. So unlike the regular displacement in normal straight linear motion is usually represented with letter D or S for displacement. But in the case of angular displacement, it is represented with theta. It's represented with theta. Then for velocity, normal straight line motion, that's transitional motion, displacement velocity is represented with letter V, usually. With V or U, depending on the type of velocity, whether it's initial or final velocity, but mostly it's usually represented with letter V. So in the case of angular velocity, that's when you talk about something that is moving in a circular path. When you talk about angular velocity, the velocity now is no longer with the letter V. They use the letter that looks like W, but it's called omega. Some persons they call it a different name, but some places you see it as omega. So it's like W, and it represents the rate of change of angle. Displacement in angular displacement, it means the change in angle, while angular velocity is the rate of change in angle, almost similar to the same thing with displacement, change in distance, then velocity is rate of change of distance with time, that kind of stuff. So the similar principles apply here, but just that in this case, it is relating to a circle. So for angular velocity, it is called rate of change of angle. Then for angular acceleration, it is represented with the symbol alpha, and represents the rate of change of angular velocity. The rate of change of angular velocity, the rate of change of angular velocity. So these are like the foundations when you're trying to talk about angular motions. You need to know these things. So we'll be heading into the next slide to see what their formulas look like. So first off, we will look at the general formula for angular velocity. So there's actually a formula that states similar to if you look at this formula, these formulas are similar to the equations of motion, where you have V is equal to U plus AT. So it's similar to this now. V in this case now, this W is representing the final angular velocity. W naught is representing initial angular velocity. So then plus alpha, meaning our angular acceleration, then T, meaning our time. The same principle. In the same principle, we have the second one being from normal linear motion, we have S is equal to UT plus half AT squared. So now that case of S, in that case now is no longer S, now is theta is equal to W naught T, that's U plus half AT squared. So these formulas are similar to the normal formula we know. S is equal to UT plus half AT squared. V is equal to U plus AT. V squared is equal to U squared plus 2AS. So that's actually how the formula is similar to normal linear motion. So as I have here, I said these equations mirror those of linear equations, but apply to rotational objects or to rotating objects. So these formulas I think if you already know linear motion formulas, these ones will just be like a replica of those formulas. So it's important that if you're writing, just write these formulas down, because some questions you might be needing to use this formula. So let's move on. As I said, angular displacement is measured in radians, and this one is representing W, is representing the final angular velocity, and alpha is representing the angular acceleration. So now let's see the comparison between angular velocity and linear motion. That's angular motion and linear motion. So for linear motion, there's a relationship between linear motion and angular motion, and that relationship is between their velocities. So when you have the velocity of normal linear motion, V, is similar to the velocity of angular motion, in that velocity from linear motion is equal to RW, where R is known as the radius. R is the radius of the circular path that the motion is happening in. I don't know if you guys can still hear me. Can you guys hear me?
Yes, sir.
Yes, we can hear you.
Can you say the formula
Okay.
again?
Which of the formulas? Is it this one? There's a
Yes,
formula.
this
The
one
first,
that you're explaining, that you are trying to say R
okay.
equal to
Okay, the formula is that
W.
V from normal linear equation. If you compare linear equation with linear motion with angular motion, there is actually a union point or a point of union where they are equal. So linear velocity is similar to angular velocity with this expression. Linear velocity V is equal to R
So I can't
angular
see your
velocity.
screen again. Oh.
Can you see it now?
Okay. Yes, I've seen it.
Okay, so this is the formula for linear velocity. The relationship between linear velocity and angular velocity is V equals R W, where W represents the angular velocity. Normal V represents normal linear velocity. W represents angular velocity. Then we have R being the radius. So this is the relationship between linear velocity and angular velocity. Usually it is used sometimes to get some of the formula. So is this formula most of the time that you see questions coming out from? The probably will give you, they'll say the velocity of an object was so and so. Find the angular velocity of a particular object is this, and it moves along a circular path of maybe this. They will give you a length, radius. They will not tell you find its linear speed or linear velocity. So that's what we'll see down in the example. So now for linear acceleration, now we have this expression, linear acceleration. The relationship between linear acceleration and linear velocity is this expression. Linear acceleration A is equal to R this, R alpha. So if you look at this now, the formulas are just similar. Just like as we are saying, linear velocity is equal to angular velocity. But angular velocity, you will multiply angular velocity with R. The same thing with acceleration. Acceleration, normal linear acceleration is equal to angular acceleration, but just that you multiply angular acceleration with R. So that's just what is the simple expression for this. A is equal to RA, V is equal to VW. Sorry, A is equal to R alpha, V is equal to RW. So they are supposed to, assuming this R was not there, you say that the linear velocity is equal to the angular velocity and the linear acceleration is equal to the angular acceleration. But the R is the distinguishing factor between linear acceleration and angular acceleration. The product of R with the angular acceleration will give you the linear acceleration. The product of R and the linear velocity would give you R and the angular velocity will give you the linear velocity. So these two formulas are very important that you memorize them. They are not difficult to memorize, but just put them in your mind because most questions that you see in your exams will come out from using these formulas. So now let's see a typical example, JUPEB type of example. So you have a wheel of radius 0.5 meter rotates with an angular velocity of this radians. Sorry, 10 rads per second. 10 rads per second. Normally, it was normal velocity, they'll say it is meter per second. Normal velocity, they'll say it's meter per second. So now, because normal velocity is talking about displacement and displacement is measured in meters, that's why it is meter per second. But now this one is not displacement, now it's angular change in angle. And that one is measured in radians. So because of it is radians, it's now radians per second. So angular velocity, this is equal to 10 radians per second. Find its linear speed at the rim. Find its linear speed at the rim. So the formula is just, you look for this formula, we use this formula here. This V is equal to RW, then mix it together. They gave us our R, they gave us our W. So it's just a simple plug-in expression. You just put 0.5 times 10 and you'll be getting your answer to be 5 meters per second. So you can tell that though the thing is moving at an angular velocity of 10 radians per second, in linear form, the speed is 5 meters per second. So you can see questions. These are the ways you will see questions on this. They could probably omit the angular velocity and give you just the radius and also the linear velocity. And they'll tell you to find the angular velocity. Or they might even give you the linear velocity and the angular velocity and tell you to find the radius. So this is actually how questions come out from this particular portion of circular motion. So take notes. So let's move on to what we have next. So now the next thing we're talking about is torque. Torque, T-O-R-Q-U-E, represented with a Greek letter that looks like T. Torque. So torque, by definition, it is the turning effect of a force. Torque is simply defined as the turning effect of a force. So it's just like when you talk about torque, you're talking about force that is moving opposite direction but parallel to each other. Force that's moving in opposite direction but parallel to each other. So that's another, like, I don't know, a descriptive explanation of what it means. So meaning, we had like, let's use this our square now. This is our square we have here. If we wanted this now, when you talk about torque, it's just like as if this square, this our rectangle rather, this our rectangle was to experience torque force, torque. What will happen is there will be a force from up on one end acting downwards on it, and there'll be another force from this other end acting upwards on it. So the two forces are parallel to each other, but in opposite direction. I don't know whether it's making any sense.
Live example of talk.
Okay,
Like something we can relate
real
to,
life,
something we understand.
a real life example. You remember this olden days tap that is just like as if we have a single dash on top of one thing standing on top of one single stop. All these are olden days tap that looks like T.
Yes.
Yeah, olden days tap. When you try to turn the tap open, you're trying to open the tap. If you notice, one of your hand will be on one side of the T, the other hand will be on the other side. Then you twist it open. So you're applying force forward. You're applying force forward and also applying force backward at the same time. So these two directional force. Someone's mic is on, please. Could someone turn off their mic, please? The person that his mic is turned on, your mic is kind of making a kind of noise. Thank you. So this is exactly how torque is. It's just like as if you have the letter T, you have a tap that is like letter T. You're not trying to open the tap. If you want to open the tap, you put one of your hand at the front and one of the other hand at the back, the other edge, like on one edge, you put your hand at the front. On the other edge, you put your hand at the back. Then you can twist it open. So that way you're applying force forward and also backward. But because of this forward and backward force, the object would move in a circle so long as it's held to a single point. So this kind of two-way force is what they call torque. So by definition, you hear that they say it is the turning effect of force. I don't know whether you guys understand what I mean now.
Yes.
Yeah.
Okay, so that's actually a simple explanation of what torque is. When you have a single object, a straight object, that has been acted on by two forces rather, in opposite direction. Two forces in opposite direction on its edge. So that's what torque force is. So the formula for calculating the torque is this T, this funny looking T, equals to the radius times normal force sine theta. The radius times the normal force sine theta. So where T is your normal angular displacement, what we know as before. So our normal angular displacement is our T. So that's the angle between the force and the radius. So from what we have here, I said the R is the distance from the axis. So R is the distance from the center to the edge of to one of the edge of the force. Then the other center, that's the distance. The center to the edge is the distance. So just like we have this T, this letter T, sorry. You have this letter T up here. And you're trying to apply force. I don't know, this one is not as vivid as possible. But any kind of turning effect, like you're trying to turn something open, you would definitely use torque. When you are trying to, you would surely use torque. That turning, you have to use that turning effect to open something, because you'll be at the same time you're trying to move something forward, you will also be trying to move it backwards. So to calculate that torque, the formula is this we have here: T equals R F sine theta. So sometimes you might not be given the angle, or the angle might be given as 90 degrees. And when the angle is given as 90 degrees, it would neutralize this formula, or it would balance of this formula. Or the angle might be given as what they call it. If the angle is 90 degrees, it will make this sine theta 1. So in most cases, you might see the angle as 90 degrees. So let's see an example of how the equations are given in this under this talk. So say they said a wrench applies 20 Newton force at 0.3 meters from a bolt. So calculate the torque. That's what the question is. Calculate the torque. So to calculate the torque is as simple as this. The difficulty that always happens when these questions come up sometimes in physics is most of the time when you see a question, you don't really know the formula. So I always give this advice to most people that I try to explain mathematical stuff to. I always say when you have a subject or a course that has formulas, the best thing you should do for yourself is get a separate note, even if it's a 2A note. That note should just be for topic and formula, topic and formula. So that each topic you see, you should list out all the formulas in that topic. So that way you can get familiar with the topic and the formula, so that when you see a question that is relating to that topic, you could, if you are someone that has pictographic understanding, you could remember what you saw on your book. That okay, maybe you say okay, under linear motion, there were 4 formulas. Okay, there were 4 formulas. Let me see. I can remember that the first one, they asked us to look for which of these formulas looks like the one that would work in. So that way you can be able to help yourself remember, because mostly physics is not really difficult. It's not really difficult. The main thing is just if you can remember the formula, even the formula can help you know what you are supposed to look for. Maybe some cases might just be that you need to join 2 formulas together to get the final answer, but most of the times the formula would help you to know what you're looking for. So when you see a question that is probably asking you for torque, or they gave you torque, your mind should always go to this formula. C is equal to RF sometimes. But if you see angle also, you now know that you add sine theta, RF or RF sine theta. So this is the formula. So in this case now, we'll see that the answer is just simple, multiplying 0.3 times 20, and that's your answer. That's just your answer. So most people will get confused when they see torque. They've not taught us this one. But it's just something that is very simple and could have given you the mark that you are looking for. So it's just, I would advise that you guys should probably get your own yourself, probably even if it's a simple jotter. To jot each topic, you write down the formula in each topic. Then you try looking at regularly before you know, you guys, I think you guys are doing maximum of 3 subjects. 3 subjects is not really that much. If you should start early to start preparing yourself for the exams per semester with constant practice, even if you're a slow learner or you seem like as if you're a slow learner, if you continuously put your mind, even if you're dedicating at least 2-3 hours every day, just 2-3 hours every day, you should be able to hit a very good grade. As long as you keep on practicing. Sorry, because there's actually a law that would always reward you for any effort you put in. So long as you're putting in the right effort, you will definitely see the result. So let's move on to the next slide, so we'll not waste much of our time on this. So the next we have here is moment of inertia. I think that should be, I did not miss slide. Yeah, moment of inertia. So moment of inertia, by definition, is the resistance of an object to changes in its rotational motion. So as we have friction in the case of linear motion, the restriction from movement, that's the same thing as moment of inertia. That's what moment of inertia is similar to. So in the case of friction, is for translational motion, that is one directional motion, straightforward motion. But in the case of circular motion, it's not called friction per se. It has a special name. They gave it a new name, and they call that name moment of inertia. So it is the resistance of an object to its change in rotational motion. I don't know whether you guys are following me. So the similarity to friction in the case of what they call it, of rotational motion, is inertia. Is moment of inertia, not inertia, moment of inertia. So it's usually dependent on mass distribution. So what do I mean by that? It means force. And the formula, as I was saying, I said the formula is very simple. Just T is equal to RF when you are not given an angle. But when you are given an angle, or you are asked to get the angle, it's going to be T is equal to RF sine theta. So it's that simple. There is nothing to make complicated about it. It's just understand what it means. It's that turning force effect. That's the definition, or it's the force that acts on a particular object parallel to each other but in opposite direction. So usually you see the question typically appearing in this form, where they would ask you, they'll give you a force and they'll give you distance, and they'll tell you to find the torque, or they could give you the torque and tell you to find the force, or they could give you the torque, the force, the radius, and tell you to find the displacement, or the angular displacement rather. So it's just as simple as that. Just once you know the formula, you're good to go. Once you know the formula, you're good to go. So let's move on to moment of inertia. So as I was saying, I said moment of inertia is similar to friction. Just that friction, on what we know, is generally for motion. It's for almost all forms of motion. So, and it is seen as the force that tends to oppose motion generally. That's what friction is. So moment of inertia is kind of like a kind of friction in the case of circular motion. A kind of friction, or the name given to the kind of friction under circular motion. So that kind of friction, that is the resistance of an object to move in circular or change its rotational motion, is what they call the moment of inertia. So from what I have here, I said moment of inertia is the resistance of an object to change its rotational motion. So as when you were trying to spin, you were spinning, maybe you held let me say you held a shoe by its lace. The shoe was laced up. You held the shoe by its lace and started spinning it on the air. The resistance to stop, like if as you're spinning it clockwise, you're continuously spinning it clockwise. If you wanted to spin it backwards, that resistance that you experience to try to stop it, that is trying to oppose it from moving, changing its rotational direction, is what they call the moment of inertia. So that's what they call it in a physics term. Moment of inertia is that resistance of an object to change its rotational motion. So I don't know. I hope you guys are following me. Okay. So now, after we've explained what this moment of inertia is, so now there is this there is a principle. I don't know if I'll call it the principle that kind of applies to moment of inertia. They said where there is more weight, there will be more moment of inertia. So on an object, as we had maybe a hammer, like an hammer, the portion of that hammer, if we were to spin the hammer, the portion of that hammer that would have more moment of inertia is the place that has heavier weight. So that's just one extra thing you should know about moment of inertia, because you might see it as, say, which of these statements is true about moment of inertia. Increased mass leads to increased moment of inertia. Then they will start talking all the other rubbish that they feel they should to confuse you. So just know that the larger the mass, the larger the moment of inertia. So the moment of inertia has a direct relationship with the mass of an object. So you can even see it from the formula. So the general formula for moment of inertia is given as this for a point mass. That is for a very tiny mass. It is given as this for a tiny, like a single dot kind of object. The formula is I, where I is representing the moment of inertia, equal to the mass of the object times the radius of its motion squared. I is equal to mr squared for a point mass. That's when an object, just maybe a point mass is something that looks like a single object that's probably circular at a spot. Is what they call like a point mass. It's what they can call a point mass. Maybe a single object that does not have a kind of different geometry, like an object that is whole, like a ball. You can classify a ball as a point mass. So point masses are objects that their mass is kind of singular, like their mass is kind of singular. It has a single direction. So the formula, when it is in that case, is going to be simply I equals to m times r squared. I is equals to m times r squared, where I is the moment of inertia, m is normal mass, r is the radius of the motion, of circular motion. So then in the case of objects that look like disc or a ring, or I think I was still at the moment of inertia. I think that was where I was at. So I was
Yes,
saying
sir.
that we have the moment of inertia for two types of, I don't know, is she the only one on the call? Can other people hear me? So I don't know whether it's just my
I
network
can
that
hear
has
you.
the issue. Okay, thank God. So we have two major types of formulas for the moment of inertia. So depending on the structure of the object that you're trying to measure its moment of inertia. So when the object is ring-like or like a solid disk, the moment of inertia formula will be I equals half mr squared. I equals half mr squared. So this is the formula here. I is equals half mr squared, just similar to the formula for what they call kinetic energy. So I is equal to half mr squared. So this is when the case of the object is like a solid disk object or ring-like object. So that's for moment of inertia. Let's move on to rotational motion equation. So these are generalized equations that try to relate moment of inertia, torque, and also angular velocity. So that the formula that tries to relate it together. We're talking about in normal force, according to normal Newton's law, there's a force formula that says F is equal to mass times acceleration. F is equal to mass acceleration. So there's a similar formula to that in the case of rotational motion. And that formula is the torque is equal to the inertia times the angular acceleration. So that's what we have here. The torque is equal to I alpha. Torque is equal to I alpha. So these formulas are similar to normal linear equations. So they are similar in a way. Torque is a force, a kind of force. Moment of inertia is a kind of resistance related to mass somehow. Then we also have what they call it, angular velocity representing the A also. So as we can see, normal formulas for linear equation, we have F for representing F. In the case of circular motion, we have torque representing F. So representing mass, in the case of linear equation, we have I, that's moment of inertia. Representing acceleration, we have angular acceleration. So this formula is the formula that is similar for rotational motion. If you're trying to check the force, or you have an expression where they give you formulas, or you're asked to calculate maybe one of the parameters for angular or circular motion, this formula is going to come in handy to you. So we've seen that the basic laws of motion, the basic equation of motion, that's v squared is equal to u squared plus 2as, s is equal to ut plus half at squared, v is equal to u plus at. They have their expression in circular motion. The same thing, we also have force having its own similar expression also. So this is the expression for force now here, where we have torque is equal to moment of inertia times angular acceleration. So the formula is that simple, and questions would always come in this form. So this particular portion of physics is one of the simplest portion of physics, where the questions are usually direct, especially for Nigerian studies. The questions are usually direct under this topic. They barely would twist it. If they will run twist, maybe they will merge two formulas. Let's assume they wanted to get the displacements. They could give you torque and they'll give you moment of inertia and maybe acceleration, or they'll give you torque and moment of inertia. Then you now need to find the acceleration. Then you relate it back to the first formula, those first formulas we had, to find maybe the displacement. So, but usually the formulas are just simple. They're not really having much moving parts, just as simple as normal linear equations or the equations of motion. So if you can memorize these formulas, I'm saying again, if you can memorize these formulas, it will help you a long way in solving most of these kind of questions. So the formula for the relationship between torque and angular velocity is given by this expression. Torque equals moment of inertia times angular acceleration. So the questions will be like this. Just they could ask you to look for the angular acceleration, or they will tell you to look for the torque, and they'll give you the other parameters. So it's just as simple as this. So let's move on to the next parameter that we'll be talking about under circular motion. The next parameter is centripetal force. Centripetal force. So I know we've heard about centripetal force severally, probably in one of our classes when we're talking about escape velocity and satellites in motion. We're talking about objects that are moving around around an orbit. We mentioned centripetal force. So when we have this centripetal force now, by definition, it is the force that is said to keep an object in circular motion. Centripetal force is the force that is said to keep an object in circular motion. So now we have normal straight force, linear force. So we also have centripetal force. So it's different from torque. Centripetal force is different from torque. So the formula for the centripetal force is Fc. This C can be in subscript, can be a subscript. F subscript C is equal to mv squared over r. Fc is equal to mv squared over r. So this is the formula for centripetal force, where our m is normal mass, v is normal linear velocity, v is normal linear velocity, not angular velocity now, linear velocity. So, but if you want to get the expression for centripetal force in terms of angular velocity, this is the formula. The formula is going to be Fc equals to mr this, mrw squared. So this is the formula for centripetal force in terms of angular velocity. So I think most of the things you'll be doing in this class is just writing definitions, understanding the concept, and also writing the formulas, because it's as simple as that. For this week's topic is just as simple as that. Just writing equations, understanding the formula, understanding the concept, and I think that's how simple it is. So for centripetal force, we have two formulas: the linear equation formula, and also the involves the angular motion velocity or the angular velocity. So the formulas are this: Fc equals this expression, or Fc is equals this expression. So from this expression now, we can, in case we can merge these two equations, this mv squared over r and mr over c squared, we can equate both of them together. Since Fc is equal to both of them, we can say we equate both of them together, and we equate both of them together, we will get back that initial relationship between velocity, linear velocity, and angular velocity. Because when we equate them together, m will cancel out m, r will increase by itself, making it r squared. Then v squared will be here. Then when you take square root of both sides, you will find out that you have v is equal to rw. V is equal to rw. So this was actually one of the formulas that they used to prove that v, as the linear velocity, is equal to r angular velocity. So the centripetal force is what is like that expression that was used to determine that formula. This formula being equal to this formula. When you equate them together, you'll be having mv squared over r equals mr w squared. So when you cross multiply, you would have r will multiply, making this r here now r squared. So you're having mv squared is equal to mr squared w squared. So when you cancel out m, you'll be left with v squared on one side, you have r squared on the other side. So when you take square root of both sides, you then be left with v equals to r w squared. So that's how they got that first expression. I don't know whether you guys are following me. Can you guys still hear me?
No, Sam, I do understand it too.
Okay. Can you still hear me?
Yes, sir.
I can hear you.
Okay, so the formula is centripetal force is equal to mv squared. There are two formulas that I just mentioned, mv squared over r, and also mrw squared. So now these two formulas are important, or they are complementary. You could use each of them to get your centripetal force depending on what you are given. If you are given the linear velocity v, you use this first formula. If you are given the angular velocity, you use this next formula. So in the case of finding where they did not give you, maybe they did not give you, they gave you v, or it's not even necessary self. Since you remember the formula that says v is equal to rw, the relationship between v and the relationship between linear velocity and angular velocity, it was this formula that they used to get the expression for the relationship between linear velocity and angular velocity. So how did they get it? They equated, since this fc is equal to this and fc is also equal to this, they just equated both of them. Since if this is equal to this and this is equal to this, that means this one will be equal to this one. So when you equate it like that, if you try to make v subject of formula, you will find out that you'll be left with just v equals rw. If you should do the math, you end up seeing that you're left with just v equals rw. So that's what I'm just trying to explain. So when you talk about centripetal force, you should always note that the direction of centripetal force is always towards the center.
I didn't understand how you canceled it.
Okay, write on your paper mv squared over r on one side and write equals to mrw squared on the other side.
I've written.
mv squared over r is equal to mrw squared. So then next, cancel m on both sides. You'll be left with v squared over r. You'll be left with v squared over r equals rw squared, right?
Yes.
So then now multiply both, that is cross multiply, you'll be having V squared is equals to R squared W squared, correct?
Pardon?
If you
I
cross
should
multiply,
cross
you'll be having,
multiply.
yeah, you'll be having V squared is equal to R squared W squared, right?
Yes, yes.
Yeah, so now you can now take square root of both sides. So if you take square root of both sides, V squared will turn to V, R squared will turn to R, W squared will turn to W. So you now be left with V is equal to RW. So that's the same relationship formula that we were talking about at the beginning of this lesson. We were talking about the relationship between linear velocity and angular velocity. So that's what I was trying to drive at.
So V will now be square root of
Equal
R
to
squared W
W
squared.
squared. And that will be
Okay.
equal to, V will now be equal to RW, because square root of R squared is R, square root of W squared is W. So V will now be equal to RW. I hope it's clear now.
Yes, sir. Thank you, sir.
Okay, you're welcome. So now let's move on to what I was saying. The direction of centripetal force. So these things are things that you should just take note of. These definitions that I highlighted here. Centripetal force is actually the force that keeps an object in circular motion. Is the force that keeps an object in circular motion, and that force is always inwards towards the circle of the circular part that the object is moving. So if an object is moving around a circle, the centripetal force that is keeping that object to continuously move around that circle is always pointing inwards to the center of that circle. So that's what this sentence is saying. The direction of centripetal force is always inwards towards the center of the circle. And without this centripetal force, the object would not stay in circular motion. If there is no centripetal force, an object cannot stay in circular motion. Instead, the object will move in linear motion. It will move on a straight line, because that force is always what is keeping it within that axis. So if that force does not exist, that object will move in a single line, or that is on a straight line. So centripetal force is what keeps an object in motion. Without centripetal force, an object will not stay in a circular motion. And the direction of centripetal force is always inward toward the center of the circle or the circular part. So with that said, let's move on to the next slide. Applications of centripetal force. So where do we apply this force? So centripetal force is applied in making turns on road. If you guys are people that watch Fast and Furious, you remember all these drifts where you see a car will be moving, and when it wants to make a sharp curve, it would ski across the curved path. So it's usually based on centripetal force, the force that is keeping it. The driver will always try to keep the car. He'll be trying to force the car to stay in the center, that's towards the curve that is trying to come in. So that way, it's creating a centripetal force, trying to keep the object in a circular path or in a curved path. So that's one of the applications of centripetal force. So in clothes spinning in washing machine, there is actually washing machine. If you've used washing machine before, you see that the object, the clothes, they continuously spin inside the washing machine. So what makes it be that even when you leave the washing machine open, the only thing that would splash out is water, is because of this centripetal force that these objects are moving in. There would barely be a reason for the clothes to spin off and fly out of the washing machine. They would continuously be moving within that circular path. So these are one of the applications of centripetal force. Another major application is in satellites. NASA, they use it a lot. All these people that send objects to space, there is how they calculate it to send the object outside in space. They will measure the escape velocity, measure the centripetal force that should be generated, and they will launch the rocket or the satellite into space. And once they've launched it, usually it's specifically for satellites, because satellites are expected to move in circular motion throughout. They're expected to move in circular motion. So if you want to send an object in circular motion, you take note of things like the mass of that object, the speed at which that object must move, and the distance that the object will move from the center to the distance you want it to stay in that circle. So I think this is even the same thing that is applied in I'm not sure, but boomerang, all these boomerang objects. There is a level of circular motion principles that is applied in the carving of these objects, so that it would keep them in circular motion. So this force the force that keeps those objects in circular motion is called the centripetal force. So this is how you see formula for centripetal force. You see question, sorry, in centripetal force in your JUPEB past question. You see it like they could give you the mass, give you the normal linear velocity and the radius, and they will tell you to find the centripetal force. So if you don't know the formula, you might start thinking that is something that you don't know. But as I said, in this aspect of physics, the formula is what actually matters. The formula, the understanding of the definitions, and some common principles that applies to this formula. If you can memorize if you can have this scope in your mind for each of the topics, each of the contents I'm mentioning since the beginning of this class, I can say you've covered this thing to a large extent. You've covered this topic to 75%. So the remaining 25% will be left to your own ability to blend formulas together to get the final answer. So these questions I've been giving so far are just straightforward questions where they'll just give you one missing parameter, they'll give you the other ones that you know, and you merge them together. But in exam cases, you can see it like that, but you could also see some where they would merge two formulas together, where you use one formula to get one parameter, and that parameter you've got to use to go and apply in another formula to get your final answer. So this is actually how the questions come out generally. So this question we are given that a 2 kg mass object moves at 4 meters per second. So when you see meters per second for velocity, you know that it is the linear velocity, that it is v. When you see meters per second, you know that it is the linear velocity, that is the velocity v. But when you see rads per second, take note of the unit. When you see rads per second, know that they are giving you the angular velocity. When you see rads per second, know that they are giving you the angular velocity. Sorry,
Take it
sorry
so
about
that we get the difference explaining now, because it's very important.
Okay, sorry about that. We
No
have
problem.
this is how the formula comes out. These are the questions come out. You will be given sometimes mass or some other parameters in the formula. First, you need to know the formula. Then once you've known the formula, you will start checking what you were given. So this question, they gave us a 2 kg mass object. We've known that they're giving us mass, moves at 4 meters per second. So now, normally this thing is velocity. They could say moves at a velocity or moves at a speed. If you see meters per second, we know generally that speed is measured in meters per second or velocity is measured in meters per second. So when you see meters per second representing speed or velocity, just know that you are using this centripetal force formula.
When you see meter per second.
Yes, you know that we are using the formula that has V, because V is only applicable when you are giving velocity
That
in
is
meters per
what
second.
we used before. When we see this M.
When you see meters per second, when you see meter per second, know that it is velocity. That you're using the V formula. But when you see rads per second, when you see rads per second, you know that you're using angular velocity. And in that case, you use this formula instead. The same FC you're looking for, but you use this formula here. You use this formula, FC is equal to mRW squared, where that rads per second is your W. Your W is always measured in rads per second. W is always measured in rads per second, while velocity is always measured in meters per second. So depending on the parameters they give you, you will choose the formula you use. So if they ask you to find the angular velocity, you know that normally you're supposed to use this angular velocity formula. If they ask you to find the force, you know that you're possibly going to use either of the two formulas. So depending on which parameters they gave you, if they gave you velocity, you know you're using the one that has velocity. If they gave you angular velocity, you know that you're using the one that has angular velocity. So this question now, we are given normal velocity, 4 meters per second. So we know we are using the formula that has normal velocity.
And that one is linear velocity. The 4 meters per second is linear velocity.
Yes, whenever you see meters per second, is linear velocity, not angular or circular velocity. So it's linear velocity. So now that's for this. So just calculating this, you'd have this as the full expression, and you can get your final answer by normal mass, 2 times 16 divided by 2, or 2 times 4 squared divided by 2, and you get your final answer as 16. So now let's move on to one of the last topics for today, and it's on simple harmonic motion, usually written as SHM. So whenever you see SHM, it means simple harmonic motion, especially in physics. Under physics, and you're hearing stuff about circular motion, or they're mentioning stuff about rotational motion, and they now write SHM. They're talking about simple harmonic motion. So what is simple harmonic motion? This is a kind of oscillatory motion. It's a form of oscillatory motion where an object moves to and fro, to and fro. It moves from a particular point to another point, returning back to that initial point. So it's a to and fro kind of movement. A simple harmonic motion is, example is all these I think bell, all this bell you see in the Catholic Church, where it would start, someone will just dangle it and to moving, be slamming one side, slamming the next side. So those kind of periodic motion is called simple harmonic motion. So simple harmonic motion is a kind of periodic motion or oscillatory motion where the restoring force is directly proportional to displacement. So simple harmonic motion is an oscillatory motion. It's an oscillatory kind of motion where the restoring force is directly proportional to displacement and it acts in opposite direction. So that's the simple thing. So like the simple pendulum stuff I was mentioning in one of our classes, I said simple pendulum bulb. If you've seen their experiments real life, you will see that they'll just tie this pendulum bulb with a thread and hang it to maybe to a nail on the wall or something, or to a standing G clamp. They will tie it to that and they would pull the pendulum bulb. They will allow it to stretch downwards and they will pull it backwards to a particular distance and leave it, let it just keep dangling. It's dangling left to right, to left, to right. That kind of oscillatory motion, to and fro movement, is what they call simple harmonic motion. It's the same thing that is seen in springs, when probably you hang a mass on a spring. Maybe you hang an heavy object on a spring and just let the object drop. You will see that the object will keep on bouncing up and down, up and down, up and down. That kind of motion is also an example of simple harmonic motion. So it's usually a kind of oscillatory motion, that is a to and fro motion, where the restoring force is directly proportional to the displacement and it acts in opposite direction. That is, acts to and fro. So if it's up and down, it's moving, it's continuously move up and down and up and down and up. If it is left and right, it's continuously move left and right and left and right and left. So that's one of the characteristics of simple harmonic motion. They always move continuously in opposite direction after they've reached a particular distance or covered a particular displacement. So they're usually, if you're talking about simple harmonic motion in terms of a simple pendulum bulb, there will usually be an angle. There will usually be an angle. Let's go to the next slide and see some mathematical models when you're talking about simple harmonic motion. So for simple harmonic motion, the force for simple harmonic motion is measured with the formula minus kx, where k is a constant. K is a constant that is related to either the spring or the wire or whatsoever object that is holding the object that is moving. So k is a constant that is dependent on the object material that's keeping the object in motion. So k is a constant, either spring constant. F is the force. Then x represents the displacement of that object from its equilibrium point. That is distance the object covers from its initial starting point till the maximum distance it covered. So as we had a simple pendulum bulb, we are using a simple pendulum bulb now. When it's at rest, to be straight. So the movement, when you want to move it, the simple pendulum bulb, you will move it back to a particular extent. So that distance you've covered away from the starting point is what they call the displacement. So that's what they represent as x. So another formula that is used in calculation during in simple harmonic motion is the formula for acceleration, and the acceleration formula is given as a equals sorry, a is equal to minus w squared x. A is equal to minus w squared x. A is equal to minus w squared x. So for simple
So
harmonic
what
motion,
you
when you
say is x
x is
in the first
displacement.
formula, FC.
The
In that
same thing
formula,
is the
FC.
same thing everywhere. Is the same
Pardon?
thing everywhere. Is displacement. Displacement.
Okay,
X is displacement.
displacement.
Yeah.
Okay,
So X is
why is it
displacement.
that the first sign has a negative sign?
It's because usually the motion is always having an opposite direction. Like you cannot tell whether it's negative or positive. So it is usually a flickering motion. So that's the reason for negative sign. Negative sign is not really meaning the magnitude of force, but because it is a flip-flap motion, kind of, that negative sign is just indicating that's what it's indicating. It's not really a value-related stuff, it's a direction-related stuff. So the negative sign is indicating that it's a directional stuff. So A is equal to minus W squared X. So then the X on its own now has an expression that is given as A cos WT plus omega. So where our A is representing the amplitude, we'll move to where we'll explain what this amplitude is. A is representing the amplitude. Just write what you're saying. Later we'll explain what it means. So we have amplitude for A. We have our normal W. We know W as angular velocity. Then we have a new parameter. We have two new parameters. W now, in this case, this new parameter is called phi, phi, and it's known as the phase constant. The phase constant. So this is the expression for displacement. So now we are not talking about angular displacement now. And we're not talking about circular motion now. We're talking about oscillatory motion. We're talking about oscillatory motion. So oscillatory motion is different from
The phi is what?
phase constant. It's down here. Phase constant. See it here.
Pardon?
Phase constant. See it here. Phase constant. I've highlighted it here. Phase. Yeah, this is it here. Phase constant.
Is that?
Yeah, that's phase constant. Phi is the symbol is a Greek symbol called phi. As we have pi, pi for normal pi, we know we have this one as phi, phi.
Okay, I've seen it.
So that's how so the phase constant. So now this is the formula for displacement under oscillatory motion. So displacement under oscillatory motion that is given as x. Displacement under circular motion is given as angular displacement or change in angle, yeah. And is represented with theta for circular motion. Displacement in circular motion is represented with theta. Take note. Displacement in circular motion is represented with theta. Displacement in circular motion is represented with theta. But for simple harmonic motion or oscillatory motions, it is represented with x, and the formula is given as x is equal to a cos wt plus phi. So this is the expression for displacement under simple harmonic motion. So write it down in your notes. So, and in this case now, our W in this case now, in normal circular motion, our W is usually called, it's on the screen. It's on the screen. A displacement is equal to this. This is the expression I'm talking about.
There's explanation you gave there, which I didn't get.
I don't think I gave an explanation. I said when you are given in displacement in simple harmonic motion is given by this expression. While displacement in circular motion is represented with theta. And I gave the formula initially at the beginning. So now for circular motion, for oscillatory motion, that is simple harmonic motion, the expression for displacement is given as this. And this W in this case now for simple harmonic motion is not angular velocity. It's not called angular velocity, but in this case, in case of simple harmonic motion or oscillatory motion, in this case, it is not called angular velocity. It is called angular frequency. Angular frequency. Angular frequency. So take note. In this case, it is called angular frequency. So we've talked about circular motion and we are done with circular motion. Now we are into simple harmonic motion, which is also known as oscillatory motion. So now some of the parameters are changing. For circular motion, we had force, and the relationship with force was torque. And we said the expression for torque was IA or I alpha. So now, in this case now, we have simple harmonic motion, and the force for this simple harmonic motion is minus kx, right? So now, the same thing, we also have acceleration to having its own expression. So this W in simple harmonic motion is not the same W in circular motion. In circular motion, it is called angular velocity, but in this case, it is called angular frequency. Angular frequency. So now let's move on to the different graphs that tries to explain a typical simple harmonic motion. Different graphs that try to express the typical simple harmonic motion.
Hello, sir.
So
Please
these are
don't
two.
be. Hello, sir. Please don't be offended, though. Let me
I can hear
take
you.
you aback. Yes, you said that the W in this simple harmonic is angular frequency.
Yeah. Yeah.
I didn't get that side.
Angular frequency is different from angular velocity. It's different from angular velocity. So I'm about to explain angular frequency. So angular frequency is something that is related to simple harmonic motion. It's a parameter that is related to just simple harmonic motion, or usually simple harmonic motion, while angular velocity is a parameter that is related to circular motion. So the topic of this week is circular motion and oscillatory motion. I think that's what it is. Circular motion and simple harmonic motion. I think either one of those two. So we are done with circular motion, and now we are into simple harmonic motion. So now some of these parameters are changing. We have W in circular motion, but the meaning for W in circular motion is angular velocity. But in this case, it is angular frequency. It is angular frequency.
Well
So now I'm trying to
understood.
explain. So now I'm trying to explain now the graphs of simple harmonic motion. So we have a velocity time graph, and we have an acceleration time graph. We also have a distance time graph or a displacement time graph too, but mostly I'll be explaining just this two. We have three types of graphs: displacement time graph, distance time graph, sorry, displacement time graph, velocity time graph, and acceleration time graph. So for a displacement time graph, it's known as it usually has the form of a cosine wave. I don't know if you guys already know what a cosine wave is, but a cosine wave is the one that, if this is the wave now, if this is the wave, this is the beginning. You see this broken line here on this our diagram, this broken line, not the first line at the beginning, or the broken line after the first line. It's assumed as the zero line usually. In most of the textbook you will not see it as like this diagram. You see it like this. That this is this first line will not be there. It's just be like as it is the line. So a cosine graph is one that it starts from 1, goes down to 0. Then after 0, it goes down to -1, comes back to 0, goes back to 1, comes back to 0, goes down to -1, comes back to 0. So this is how a cosine graph is. Take note, the cosine graph always starts from 1, goes down to 0, then down to -1, back to 0, up to 1. So it's just, this is how it moves. It moves starting from 1, down to -1, up to 1, down to -1. So that's how a cosine graph is. And this is, when you see that kind of graph, it is talking about a displacement graph, a displacement time graph. When you see a cosine wave, it's a displacement time graph. So for velocity time graph, when it's a velocity time graph, how it look like is it will start from 0 down to -1, up to 1, down to -1, up to 1. That's how it moves. It starts from 0 to -1 to 1 to -1 to 1. So that's how the movement of sine graph is. Just take note of this thing, because you could see it in exams where they will give you different graphs and they'll tell you which of them is the displacement time graph under simple harmonic motion, which of them is the velocity time graph under simple harmonic motion. So your understanding of sine and cosine waves or sine and cosine graph would help you or would guide you on picking which one is the correct one. So you will need to know there are 3 types of graph. We have the displacement time, velocity time, acceleration time. So displacement time is a cosine graph. Velocity time is a sine graph. Acceleration time is an inverted cosine graph. So for normal cosine graph, it starts from 1 down to -1. From 1 down to -1. That's where the thing begins. From 1 down to -1, back to 1, down to -1, back to 1. That's how it's moving. So, but for a velocity time graph, it starts from 0 down to -1, 0 -1 1. That's how its movement moves. It moves 0 -1 1,
So I'm
0
confused.
-1 1. You see this graph here? Can you see this graph here?
I'm feeling you are too
You see my-
fast. I'm not getting what you are saying.
Can you see my cursor? Are you seeing my cursor here?
It's very tiny. I have a very good eyesight.
So you can see this now. We have 3
Yes.
graphs here. We have 3 graphs here. This first graph, you see this line here, this broken, after this first line at this point here, there's a next line that is broken line here. Are you seeing this?
Yes.
So this broken line is where I'm talking about, that is usually the beginning line.
It's what?
Usually the beginning line is like the
Okay.
starting point. Is the starting point usually. So for a displacement time graph, can other people hear me?
Yes, sir.
Yes, sir.
Okay, so for a displacement time graph, it always starts from this top. So usually they will call these points, this upside of this beginning line, they will always call it, here they call it xi. Usually in normal cosine or sine, it's usually number 1, they will call it. So it will start from 1 and go down. You see how it moved down to 0. This is 0 line. This straight line is 0 line. So it will start from 1, go down to 0, come down to another 1 here. Now, when you go down below, it's minus now. So normally it's supposed to be minus xi that will be here. So the point that this thing will stop here, the point that this one will stop here is minus xi or -1. So that's why I'm using 1, so it not be confusing. So I'll use the maximum point here as 1 and the minimum point here as -1. Maximum point as 1, minimum point as -1. So for a cosine graph or a displacement time graph, cosine graph is equal to displacement time graph. It starts from, you always start your beginning when you draw this cross now, you would always start your beginning from up, coming down, going back up, coming down, going back up. It can continue as long as possible. But the main thing about it is, you know that it starts from up. That's the main thing about it. It starts from up. It starts from up. It starts from up. That's for a displacement time graph. It starts from up above the 0 line. This is the 0 line. Above the 0 line is where it starts from. So then it comes down to 0 and goes under and goes off back and come under again. So that's how a displacement time graph is. It moves like a cosine graph. So now, going to a velocity time graph. It starts from 0. This broken line here, you see this broken line started from this 0 line. Someone is not following. So what it is this point here. See my cursor here. My cursor is here on the left. So it's going down to the middle graph. It's on the middle graph at the beginning of the orange line of the middle graph. That's where my cursor is now.
On the first graph,
The second graph.
hello, sir.
Yeah.
I've not understood the first one. You've entered the second.
Okay, see what will happen. Draw something that looks like a T that is lying down. Just draw something like a T that is lying down. One straight line, then from the middle, that is one vertical line. Then from the middle of that vertical line, draw an horizontal line. Have you drawn it?
Yes.
So once you've drawn that, mark the place where the vertical line and the horizontal line intersect. Call it 0. Then above, call 1. Mark
I can't see your
1.1.
screen again.
Don't use my screen. Use what is on your book now. I'm trying to explain what is on my screen now, but I'm trying to give it to you on your book. So now you've drawn the T,
It's not
right?
in my book now. The graph is.
I'm telling you to get a pen and paper so that I will tell you what to draw. So that I will use what is in your book now to explain it to you. Because I think you are not seeing my screen clearly. So draw T that is lying down, or draw a vertical line and an horizontal line. A vertical line, then from the center of the vertical line, draw the horizontal line. Once you've drawn it, the place where the vertical and horizontal line meet, call it 0.
Yes.
Then from 0 upward, mark a point and call it A.
I'm calling it what? O.
And call it letter A, A for apple, A.
Okay.
Then under the 0, the same distance that went up for A, take that same distance downward, call it B.
Under 0.
So now you have under 0, yes, on the same vertical line, under 0, call the same distance downwards B. Have you done that?
Use the descriptions on your own so that I will follow.
You are not
I've
seeing it
drawn the
clearly.
vertical line and the horizontal line.
Yeah, where the vertical and horizontal line met, you call this 0, right?
Yes.
Then just take maybe like 1 centimeter up on the vertical line. Take 1 centimeter upwards and mark it
Yes.
and say it is A. Call it A. Upwards, call it A. On the vertical
But
line.
your own is X1.
Yes. I'll use your own to explain. I'm not using my own to explain now.
So that when I review, I will understand it.
Whether you use X1 or you use A, the main thing is I want you to understand a particular concept. That's why I'm saying you should use A. So don't use X.
I've written the
Okay,
X1.
use X1. Use X1, no problem. Use X1. Then under the 0, write minus X1. The same distance minus X1. Have you done that?
The same distance
Have you written the minus
took
X1?
above.
Yes, the same distance downward. You take it minus X1. We are behind time. I'm trying to see whether we could rush off. The same distance downward minus Xi will be X1. So now, for a displacement time graph, I'm trying to explain what you do now. For a displacement time graph now, call it displacement time graph. It will start from your movement point will start from X1 and to go down to line 0. Then go down more to reach that position of minus X1. Then you start going back up in a curve. Like this movement is in a curve pattern. So you start going down like that, taking this kind of snake-like movement, this kind of snake kind of movement. So that is how displacement time graph. The key thing to take note of is that the displacement time graph starts from the point of X1. Your starting point will be on that X1 point. You start from X1 on the dots. So then you now draw the line down, curved line downwards, going down the same way we have it on this our graph. The way it is looking like a snake. So that's how you'll be moving it like that. Do you get it now?
Graph. Yes, I got it. From your graph, the position of that X.
Yeah.
Xi. When you
yes.
It's like they're in the same height with A.
Yes. Yes, it's the same height. A
Alright.
is always the height between 0 and x1. A is always the height between 0 and x1. It's usually supposed to be the height between
X
0 and
is
x1
what?
for a cosine graph. A is
You said the
usually
A
the
is
height
what?
between 0
Amplitude.
and amplitude, yes.
Okay.
A
Okay.
is the amplitude. And usually the height between 0 and x1.
Okay.
So now once you've drawn that first graph is for displacement time graph.
Okay.
So for the second one, you do the same T kind of the T diagram now.
Oh, it
The
remains
same T
T.
diagram.
It remains T from that broken line. From that broken line to the middle of A.
Yes, that's your T. That's your
I want
T.
to.
That's your T.
Okay.
Hello? So that's your
Yes,
T.
following. And T is what?
T is the period. It's representing the period.
Okay. Okay.
T is
This
representing
I've
the period.
understood. That first graph, you said that.
We are behind time, and I'm trying to focus on handling the diagram. Because if I can explain the diagram, the key thing
Yes.
is to know how the diagrams look like. Once you know how diagrams look like, the remaining ones are just simple explanations. So that's how I'm trying to focus on the diagram, knowing what the diagram should look like. Because if it should look like, you would make mistake. So that's why I'm trying to focus on explaining the diagram. The other parameters there, we'll get to them later. But I want to take it gradually. So if I should spend time on talking about other parameters within this diagram, it would delay us and we'll not be able to get what we're supposed to get. So now let's focus on the diagram, understanding how the diagram should be drawn. So we've drawn the displacement graph now, and I said it starts from x1, going down to O, coming down as low as minus x1. That's for displacement time graph. So now when you go to velocity time graph now, you still have the same thing. The same way you drew your x graph, you draw the same thing for your v graph now. But now in the place of x1, you write v1. In the place of minus x1, you write minus v1. So, but now this graph now, it will start from O. O will be its starting point. O will be its starting point. I'm giving you the way the diagram, the way it is typically given in most cases. O will be the starting point, and to move from O downwards. It will move from O downwards to minus v1, to the depth of minus v1. Then move from minus v1 upwards to the height of minus v1, to the height of plus v1, and so on. That's how the movement is always going. But the key thing to take note of is it starts from O.
Is that place O or V1? That place the graph started.
This thing, that I think it can be misleading if you should look at this diagram. I'm trying to give you the diagram that you see in most of the textbooks, that would help you, because when they say the velocity time, the displacement time graph looks like a cosine graph, you need to understand what it means, and that is what I'm trying to explain. As I said, it starts from x1 for that one, for the cosine graph. For the other graph, for the displacement graph now, it starts from 0. As I said, the focus should not be on this edge, this last one here. From the beginning, I said the focus should be on this broken line, this second line, second vertical line. If you look at this, what I'm saying, what I'm explaining so far, you would see it on this second vertical line.
Okay.
The broken second vertical line. So the first one, it starts from the top, going down. That's for the X graph. For the V graph, it starts from the middle, going down before it starts going up. From the middle, going down before it starts going up. Then for the acceleration on, it starts from the bottom, coming up, because it's inverse. From the bottom, coming up to the top. So that's the difference between the three of them. So the three graphs are for displacement, velocity, and acceleration time graphs. So for the displacement, it looks like a sine graph. The acceleration, the velocity, looks like a, sorry, displacement looks like a cosine graph. Let me go back to the displacement like a cosine graph. displacement looks like a cosine graph. Then velocity looks like a sine graph, while acceleration looks like an inverted cosine graph. So normal cosine starts from up coming down, but this one starts from down going up. So that's why they call it the inverted cosine graph. So if you can memorize this thing, all those kind of questions where they will be giving you different graphs and say which of them represents the acceleration time graph of simple harmonic motion. Once you can know how things appear, which one is which, you'll be able to tell the one that is the correct answer. Okay, so now let's go to the parameters for this thing. The height between x1, that's the maximum height on this curve that moves. This is our orange curve that is moving. The height between the maximum points up or the maximum point downward, or the minimum point, sorry, downward, is not, and the straight horizontal line is what is known as the amplitude. Between the horizontal line and the lowest point, and between the horizontal line and the highest point, is called your amplitude, and is represented with letter A. Represented with letter A. Represented with letter A. So then now, period is represented with letter T, and it is always from the starting point of that graph till when it returns to that exact starting point again. But it is different for this velocity graph. When it has completed like one cycle, if you look at this now, this is going down, coming up. You've gotten a T. From this top, from up, down, like maximum, minimum, maximum. It has completed one cycle. That is a period. Maximum, minimum, maximum. That's a period. So now, if you start from the middle, it's going to be middle, minimum, middle, maximum, middle. So this distance is going to be the period. So the main thing, the main idea is the period is the time it takes to complete one cycle. Cycle, CYCLE. So in the displacement time graph, it's easy to understand, to identify the period. It's the same thing with the other one, but I think it's the same thing. Just use the same definition for period. The distance between two, the time taken for it to move from one peak, that is one top, to another top. The time taken for it to go from one top to another top is called a period. The time taken for it to go from one bottom to another bottom is the same period, because it will be the same time. So that's what period is. It is the time taken for it to move from one top, going down, then coming back to that top, is the period. Or from one bottom, going up, coming down back to that top, to that bottom, sorry, is what they call the period. So the period is usually the time it takes to complete one complete cycle, either from top to top or from bottom to bottom. So that's the definition for period. That's the definition for period. So now there is now an expression that says that, I don't know, can you guys hear me?
Yes, sir.
Okay. So now, I think I'll be rounding off on this portion of the lesson, because now I think I just checked my time now. My time is way behind, and there's something that I need to hop into. I don't know how we used to cope for this stuff. Last time I said I would do this thing, I would do a video description or something, but I didn't even remember, and I don't think anybody dropped a message to remind me on that group. My bad, and I think I'm very sorry for that. If anybody can still remember what I said I would drop a video about, just help me, remind me on the group, on our group, so I'll remember and I'll drop that video. So for this now, I've explained what the amplitude is. From the horizontal line to the highest top is the amplitude, or from the horizontal line to the lowest bottom is called the amplitude. So now, when it's in a velocity time graph, the amplitude is equal to the maximum velocity. When it's in a velocity time graph, the amplitude is equal to, sorry, the amplitude and the velocity has an expression. the amplitude has an expression with velocity when it is in a velocity time graph. And the expression is that the maximum velocity is equal to angular frequency times A, that's WA. Maximum velocity is equal to WA for a velocity time graph. Maximum velocity is equal to WA for a velocity time graph. For an acceleration time graph, maximum acceleration is equal to W squared A. For a velocity time graph, maximum velocity is equal to WA. But for an acceleration time graph, maximum acceleration is equal to W squared A. So these are the parameters that you can find on a simple harmonic motion graph. These are the parameters you find on a simple harmonic motion graph. And I think these portions are very important somehow, to some extent. Mostly you not really see much questions from this topic, but it's just good to know them, because who knows, it could pop up as one of the questions that you might just need to get a reasonable mark. So just know that the maximum velocity is equal to WA for simple harmonic motion, and the maximum acceleration is equal to W squared A. We had this expression for acceleration, W squared A, so it is similar to what we have here, W squared A, but now in this case it is maximum acceleration on this kind of graph. Maximum acceleration is going to be completely equal to W squared A. It could be equal to minus W squared A when it's in the downward direction, but when it's in the upward direction, it's going to be equal to W squared A. So, but that one is just, the main idea is just know that the maximum acceleration is equal to W squared A. The maximum velocity is equal to WA. So I think that's where we would call it a night for this evening.
You are calling, is it omega?
Yes, it's omega. It's omega.
Okay.
So I think that's where I'll be drawing the curtain for this evening's lesson, because of time. We have examples of simple harmonic motion and the applications, and we also have simple pendulum bob, the basis of simple pendulum bob and how it's applied. This one's actually practical, supposed to be practical. So this is the experiment, and for now we don't really have experiments, how to carry out physical experiment for now, but there might be a time where we would do virtual experiments, probably through video on, probably, we don't know. But for now, I'm just saying, hopefully we might get a practical class, probably. So then I think that should be all for this lesson. That should be all for this lesson. The applications of simple harmonic motion is in pendulum motion, mass spring, and in a tuning fork. So this formula is the same as what we have before. It's similar to what we have before, where they gave us this is for a spring, an expression for a spring. But in the next class, I think we'll talk about that in the next class. We will explain the formula, but this is a standard formula to check for the angular frequency when you're talking about spring. It is root k over m, but so I will not just rush. At the beginning of this class, I asked whether there was a question from the previous class, but I did not get a response. Probably would have started from there. But in the next class, any of your questions that you have, just keep your question and write it down. I don't know whether you guys have your own personal notes for some of these classes, but I think you should take it seriously and probably get a note for yourselves so that you could reference what we are saying. So I think that will be all for this night class. Does anyone have any other question? I think maybe one or two questions. Any other question?
We would like you to upload the slides for us.
Okay, I would do that. I'll upload it as a PDF. I'll upload it as a PDF
Yes.
immediately after this class.
Okay.
And in case I did not happen to answer your question, or probably I did not really pay attention to your question like that, please, as much as we are trying to explain this stuff, there's actually sometimes I would stay till longer time, but sometimes if there's an engagement, I don't need to encroach into the time. So I just hope that you guys try and understand me, please. I also that you try and understand me. And this is like me apologizing for anybody that probably I did not really respond to them or respond to their question. So my apologies, please. So
No problem.
thank you all for
Yeah,
attending.
thank you,
Thank
sir.
you all for attending. Yeah,
Thank
and good night.